Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight is one of the students who works at the Planetarium. Familiar face if you've been here before, but I will still let him introduce himself.
Hi there. My name is Eli. I'm a physics and astronomy undergrad at UNB.
So we've got a super fun and not at all scary or morbid show for you tonight called Doomsday Earth, which is what it sounds like, all of the possible ways that Earth could be destroyed. Although this is meant to be a kind of lighthearted, fun show. This is in no way like we're in serious danger type thing. We just thought it's a fun topic. We'll see if you agree with us. All right, so Eli is going to be leading us through the show tonight. I'm going to keep an eye on the comments. So if you have any questions throughout the show, just go ahead and leave them down there, and I will let Eli know as those come up. With that, I will turn it over to you, Eli.
Awesome. All right. Well, again, let me make
Oh,
sure.
I
Oh,
need to turn on screen share because I forgot. You think after a year and a half I would do this.
so let me know if the window is like,
Weird.
uh, yeah, or like, big enough. Because I know sometimes it looks small. Does that look okay?
Yeah, it's weird.
I can try to. How about that?
That's better. Yeah.
Okay. And it's just on the Doomsday Earth window.
Yep.
Sweet. Okay. Cool. All right. Well, welcome to Doomsday Earth. I will give a disclaimer. It's been a very long time since we ran the show. I don't know exactly how long. Jessica, do you know?
About a year.
Yeah, I was gonna say like coming up on a year probably. So it's been a minute since we've ran this show. So I might have to pause a little bit and bring memories back as I go through it. But so we're just gonna run through some possible scenarios that could yeah, I guess like you said, there's no real sugarcoating it, and Earth cause a doomsday. But like Jessica said, this isn't meant to be like frightening. It's kind of lighthearted. There's no imminent danger of these things happening. We're not worried about any of this. It's just kind of fun, lighthearted, you know, worst case scenarios, which seems kind of like a uh, contradiction. But so the first one we're going to talk about is an asteroid impact. That's probably the most popular one, at least I would think so, that people think about when they think of doomsday on planet Earth. Also, you see this amazing art right here. And we're actually going to start it off by watching a video with Bill Nye the Science Guy. So that's a good start, I think.
We've all witnessed the beauty of a shooting star, but what would happen if an asteroid was on a collision course for Earth? Could we detect it ahead of time? And more importantly, could we stop it?
I believe I have an answer. Now, you see, asteroid impacts are serious business. When I was in second grade, Miss McGonagall told us that the dinosaurs, the ancient dinosaurs, died out because they had small brains, maybe like my old boss. But even she knew that was kind of lame, that theory was nothing. It turns out, in my lifetime, people found this crater off Chicxulub, Mexico. This crater was so big. How big was it? It was so big that an asteroid hit the Earth, or impactors hit the Earth, threw so much stuff into the Earth's sky, it was bigger in diameter than the Earth itself. So the Earth was surrounded by red hot rock for weeks at a time, cooked everything. And just the animals that lived in burrows and caves, our ancestors, led to us. So, serious business. You may recall Valentine's Day 2013, Chelyabinsk, Russia. Airburst. See, if you're an asteroid and you're going 10 kilometers a second, 20 kilometers a second, and you hit the Earth's atmosphere is like concrete. It can't get out of the way. So the asteroid just explodes, an airburst. So these asteroids are serious. Most of them are very small. If you're under 10 meters in diameter, you hit the Earth's atmosphere, you burn up. Big blue streak, blue, green streak, white streak, and then humans make wishes upon you. I don't know how efficacious those wishes are, but people do that. All right, so if the asteroid starts to get bigger, starts to get into the 25 meters and the 45 meters in diameter, then you get Meteor Crater, Arizona. Wham, huge thing. That would be like a city killer or a county killer. And then when they get to be 100 meters, 140 meters, now you're into a country killer. And then they get bigger than that. It's a continent killer. Much bigger than that, and you're taking out whole races of ancient species. So, what if we found an asteroid that was headed our way? How would we find it? How would we find an asteroid headed our way? That's a good question. Well, you can use telescopes. Skilled people can point the cameras at the sky and look for fast-moving objects, objects that are crossing the Earth's orbit. But we're missing perhaps 100,000 of these things, of these county killers, city killers, country killers. So what we want to do is build a spacecraft called the Sentinel. And as we say, it's like looking for a charcoal briquette in the dark. These things are hard to find. They're tiny compared to the vastness of space. But infrared light, heat, bounces off of them. So what you'll do, you're a satellite, you're a surveying spacecraft, you'll get your back to the sun and look out from about the orbit of Venus and try to find all these asteroids. And then you find one, what do? Do you run in circles screaming? Ah! No. We've got to deflect it. Just a little, just a tiny amount. Asteroid might be going 10 kilometers a second. We want to change its speed about 2 millimeters a second. So 10 kilometers, that's 10 times 1,000 meters. That's 10,000 meters. A millimeter, that's 1,000th of a meter. So that you take the 1 over the 1,000th, it's 1,000 times 10,000. That's 10 million. You want to change its speed at 10 millionth of its total. That's not very much. But if you're an asteroid that comes in at 10,000 tons, 100,000 tons, it does take quite a bit of force to change it a 10 millionth of its speed. Okay, how do we do that? Well, the easiest way is to get a rocket, just a big rocket. Just go out there, just smack into it. Except it's in outer space, so it just goes like that. Okay, and that would change its speed a little. Now notice, everybody, what if it's not just a rock? What if it's a pile of rocks just loosely held together by primordial gravity? And so if you hit them, they'll spread out. You'll have a shower of rocks. That would be bad. So how about this? We'll get a big spacecraft that's massive spacecraft. And we'll go out there and just get near the asteroid. Just get near it. And then the mutual gravity of you, the asteroid, and me, the spacecraft, will tug the asteroid speed just a little bit, just a tiny bit, or maybe get on the other side and tug. That might work, but here's the problem. We need a huge amount of fuel for days and weeks and months and years. And what if it stops working? You can't go out there and fix it. Okay, how about this? The laser beams, a swarm of sunlight-powered lasers that are zapping the surface of the asteroid for days and weeks and months and years. Zap, 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 zap. So some asteroid, some rock is vaporizing, and the ejecta, the stuff ejected, has momentum, just like rocket fuel, just like standing on a skateboard and playing catch with a bowling ball, the way you do. And so it would then cause the asteroid to change its speed. And so you send a swarm of these laser spacecraft so that if one of them stops working, you can use the other one. Or and you can have them come in from all different angles. And what if the asteroids are regularly shaped like this? You could beam it when the thing is smooth, and then when there's a pit or an inefficient place to be beaming, you turn off. You wait for the asteroid to turn. Then you turn it back. See, everybody, just because it's unlikely doesn't mean it's not a big deal. You know, if it only happens once every few thousand years, well, if it happens on my watch, it would, as the kids say, suck. Okay, so we don't want that to happen. We want to avoid that. Asteroids are serious business, but they're exciting. Except we're in space, so it's just. Got a burning question? Well, be sure to subscribe.
Alrighty. My favorite part about that video is talking about the laser bees, because I think that idea is really cool. As has been established. A lot of impacts have happened on the surface of the Earth in its history. This is called the Sudbury impact. It was caused by a 10-kilometer wide asteroid just under 2 billion years ago, and it's the second largest impact crater in the world. That's one of those pretty disastrous impacts. After that, we have the I'm probably gonna mispronounce it, Redifort crater. This is the largest impact crater on Earth, formed over 2 billion years ago. Again, another one of the planet destroyer, well, not destroyer, but a lot of life killer. And then we've got the one that took out the dinosaurs here. This is what Bill and I was talking about in that video. It landed in the ocean, and just recently, well, recently, within the last 50 years or so, the evidence was mounted that this is what took out the dinosaurs. And like Bill and I said, when impacts like these happen, not only does it destroy the surface a fair amount, but it sends a bunch of material out into orbit around Earth, and that material blocks out the sun, which kills the plants, which kills the animals that eat the plants, which kills the animals that eat the animals. It is pretty, it's a big bummer. And like you said, the only things that survived was stuff that lived underground or in caves, like mice, stuff like that, or predecessors to mice. And we actually find that we share a lot of DNA in common with mice, incidentally. So there's some common ancestry there. There is a tool for measuring the risk that a asteroid poses to Earth, and it's called the Torino scale. And it's basically just a numbered scale that applies a risk factor to an asteroid that we spot. And this is based on the path of the asteroid, how likely it is to collide with us, how big it is, how fast it's going, how much destruction it'll cause if it does hit. And you can see here kind of in increasing order. And it also gives like a time range for how often impacts like these happen. So you see 10, this is a certain collision that will cause global climatic catastrophe, like what took out the dinosaurs. And they happen on average once every 100,000 years. At some point in our future, we're gonna be due for another one of those. So we're gonna need those laser bees to come help out. And this is just a list of close asteroid approaches that come pretty close. So you can see in 2020, 2 happened, and pretty close in space terms is still pretty far away, enough to bat an eye at, but not enough to be worried about. Usually something picks up the interest of astronomers if it's going to come in between the Earth and the Moon. That's when it's kind of something to actually keep their eyes peeled on. And that happens pretty infrequently. But we have had a couple. I remember we also had one in 2019, I think it was. Jessica, do you remember that? There was like a really big deal made out of it.
The Halloween one?
Yes, yeah.
Yeah, the
Was that
skull
2019?
asteroid that came
Yeah.
by like on Halloween. It was like the most amazing timing.
Yeah, was that 2019 or was that 2018?
I think 2019. I'm not sure. I don't
Yeah.
remember.
Anyway, it happens sometimes.
We do have a question.
Yeah.
What other things might change an asteroid's direction long before it gets close to Earth?
Whoa, that's a good question.
I think Bill
Well,
and I touched on the biggest, like it just in some way. Oh, events way out in space, not things from Earth. So that would
just
be
getting
coming
close.
closer to another planet.
Yeah. Any massive object nearby that'll tug it.
Yep. And Jupiter does that a lot. Jupiter is both responsible for swinging a lot of things out of our way so they don't end up hitting us,
Right.
but it also will occasionally swing things at us.
Yeah.
So it's kind of a love-hate relationship there with Jupiter. But it is like, other than the sun, the most dominant kind of gravitational force in our solar system. So it affects the motions of asteroids and comets quite a bit. The other thing, of course, would be getting close to the sun would do that as well.
Yep. Or just colliding with anything. But
Yep.
yeah, the laser bees are really cool. I think that idea is pretty awesome. I always have wondered too, like if it would be possible to like stick a solar sail on something coming towards us and see if that would help at all. But I'm assuming those things are moving too fast for it to matter in the first place. So,
Probably, but I think there's still just a lot of development in the solar sail idea. So, I mean, maybe.
yeah, yeah. All right, the next object of interest, or fright maybe, is supervolcanoes. We have a couple of them on Earth. One that is pretty near and dear to us is the Yellowstone supervolcano. We've got a big pot of boiling hot lava underneath Yellowstone, underneath Wyoming and Montana and wherever else Yellowstone is. That I'm not very good at geography. And that's kind of something that people are keeping their eyes on. Here is kind of a comparison between eruptions that have happened. You can see Mount St. Helens is the green, the third largest green dot down there, and then you can see like relative to it, right, the circle that it's encompassed by is a Yellowstone eruption that happened. Just over 1 million years ago, but Yellowstone has had multiple eruptions, and it's believed that it's going to have more. You can see the Yellowstone Lava Creek happened 640,000 years ago. You can see the Yellowstone Huckleberry Ridge happened 2.1 million years ago, and that one's pretty big. So there is quite a considerable volcano sitting underneath Yellowstone, and it is believed that at some point it's going to happen again. And the mechanism by which that works is really interesting. So you've got this this hotspot of magma underneath Yellowstone, and there are a couple layers of the Earth that are at play here. So you've got this basalt magma intrusion zone, and whenever the crust stretches outwards and starts to diverge from itself, and a gap forms, that magma intrusion zone starts to kind of bubble up into that space that needs to be filled, and the immense pressure builds up as that magma pushes upwards, and eventually an eruption happens. That's why when you go to Yellowstone, I don't know if anyone's ever been to Yellowstone here, but when you go to the like hot springs or like the mud pits, you can tell that that stuff is super hot, and there are like signs everywhere, like seriously, this stuff is hot, and like bison fall in, and like it's not pretty. The reason that's so hot is because there's literally magma underneath the ground. The ground is super hot because there's hot molten magma right there, and it heats that crust up quite a bit. And so that's also why the geysers happen. That's what Old Faithful is. It's water that gets heated up, that the pressure builds up and it erupts. And it's because you've got that huge basin of magma underneath it that super heats that crust. So this is a diagram that shows what the Yellowstone eruption could amount to, depending or in terms of like how it will affect the United States. So you can see this ash thickness. So let's just talk about us, for example. We've got Minneapolis, that's in the orange, that's 10 to 30 millimeters of ash. And I mean, millimeters, it maybe doesn't sound like the most, but like that's a lot, and that will really mess with ecosystems like pretty severely, actually. Kind of similar to the asteroid impact. When that much stuff gets blown into the atmosphere, it blocks the sun, and it really messes with plant life and animals that eat the plants and stuff like that. So it is pretty consequential when things like that happen, and it has been before. So you can see, I mean, ash will reach out almost to the southern tip of Florida. Like it's going to be a very wide distribution. And the only other thing I can think about is how wind will carry that as well. Because like the other thing I'm thinking about is like when Chernobyl happened, like radiation and particles went all the way, like they were detected at the western coast of the United States. So I wonder how that's going to play out at the next Yellowstone eruption. Another one that's really interesting, oopsie, next I skipped over, is magnetic field reversals. So we're going to watch another short video on this.
Not sponsored.
Not sponsored.
We can go hundreds of thousands of miles into space, but when it comes to inside the Earth, we have barely scratched the surface. Hey diggers, what's shaking? This is D News and I'm Trace. If you look down right now, you probably see the floor. But under that floor is dirt, and way under that is bedrock, and under that, hypothesis and theory. Seriously, we have gone to the moon, but the deepest we have ever been on our own planet is 2.4 miles into the crust at the Tautona mine in South Africa. What's down there? How does it affect us? New research has some insight. Scientists throughout history have mapped the inside of our planet by measuring the movement of seismic waves generated by earthquakes. Like sound waves, these are reflected and refracted, and they change speed as they pass through rocks of different densities and flows. Geologists believe as the primordial Earth cooled, heavy elements sank to the middle and lighter elements floated to the top. The result was a multi-layer planet. The crust is the top 25-ish miles, then a 1,800-mile thick inner and outer mantle made of highly pressurized superheated rock, which flows really slowly like asphalt on a hot day. Under that is an inner and outer core made of heavy metals. This is where we think our magnetic field comes from. The outer core is a hot liquid iron alloy, and the inner core is probably solid nickel and iron. Thanks to some new computer models from the University of Leeds and the Swiss Federal Institute of Technology, we've modeled the inside of the planet 100 times more accurately than ever before. The new model has revealed the moon-sized inner core is super rotating in an easterly direction, and the outer core is flowing much slower in a westerly direction. This opposing rotation is like a generator that we think creates the magnetic field of our planet called the geomagnetic dynamo. Doomsday predictors complain about this field switching or disappearing altogether, but science has shown the magnetic field has already done that. Back in 1692, Edmund Halley, like the comet, showed that the Earth's magnetic field has a westward drift. And by looking at 30,000-year-old lava flows, geologists can tell it's also drifted eastward at times. That's not really what these doomsdayers mean, though. They mean a pole swap. North becomes south, south becomes north. OMG! This has happened too. 780,000 years ago, during the Stone Age, the magnetic North Pole was actually on the bottom of the planet. Science! Now, with the help of these computer models plus centuries of seismic tests in geology, we know more about how the core of our planet works and also the magnetic field. The swapping isn't going to do anything too crazy. A switch of east-west drift ain't a big deal. We have to adjust for that anyway because the magnetic North Pole isn't perfectly aligned with the North Pole. It's drifting westward, 1 compass degree about every 5 years or so. But a switch of the north-south field would take between 1,000 and 10,000 years and would definitely affect humans. During that time, compasses wouldn't work, and scientists think our weakened magnetosphere wouldn't block cosmic particles as easily. This would cause more intense and frequent aurora, cool, but maybe other problems like ozone holes and maybe increased cancer rates. No one's exactly sure. So what do you think of this? Are you worried? Spill the...
Alrighty, so as you kind of made it out, it's a little downplayed there. The weakened Earth's magnetic field is super important to life here, and with it being messed up, that would pose a lot of problems. Just first, some context. The way we know that the magnetic field has switched is primarily by looking at, like he said, lava flow patterns. So in mid-ocean ridges, which are areas in the ocean where hot magma comes up, dries, and then starts moving outward as more magma pushes it. We can see like little particulates and like metals and like iron and stuff like that in those crust layers seem to switch directions that they're pointing every X amount of years, and that's because the magnetic field that's pulling them in that direction has flipped. So we can see like you can see like little striations that show you that they were being pulled in different directions at different times, and those are due to magnetic field reversals. And this one's kind of a lot to look at. But what he was talking about with the dynamo, he was saying that that inner core and those metallic layers spinning around each other just generate a magnetic field, and these magnetic field lines pass through the Earth, and that molten material in there moves along with that magnetic field, because a lot of that molten material is metal. Metal is often affected by magnets, and it follows that to some degree, and those moving magnetic field lines kind of drive that material into a process called convection, in which it moves upwards, and that convection can be irregular sometimes, but it follows those magnetic field lines, and that's just another piece of context for what the magnetic field does. And so here you can see just how messed up our magnetic field gets during a reversal. So you can see between reversals, north and south, pretty well established, pretty sensible, and it blocks radiation from space very well. During a reversal, not so much. It looks like a messed up pair of Apple headphones that you left in your pocket or something. And when there's not that well-defined magnetic field that drives those particles and deflects that radiation, a lot of that hits the surface of the Earth, like you said, causes cancer, causes holes in the ozone, lots of problems for us. So that's what a magnetic field reversal could do. Next one, we're going to talk about our
we do
solar
have
flare.
a question.
Oh, yeah.
That's not fully related, but they're asking, do moons have poles? And I think there's a couple of different ways to answer this, because a pole means a couple of different things. When we talk about like the North and South Pole on the Earth, what we're technically talking about are the rotation poles, kind of where if you pictured the Earth spinning with like a rod going down through the middle, that rotation axis is kind of like that pole that the Earth is spinning around. And so that's our North and South Pole, is just that rotation line. And anything that rotates has that. So moons have rotation, North and South poles. Then there's also magnetic poles, which dictate where north on a compass or south on a compass point towards. And our north magnetic pole is where we call our North Pole, but as we saw in the video, they're not perfectly aligned. So things with a magnetic field, like the Earth, like Jupiter and Saturn, Uranus and Neptune, all of these things also have a magnetic pole that sometimes are aligned with the rotation, sometimes they're not. That's actually something that scientists and astronomers are still trying to figure out, is why they do tend to be lined up, but why sometimes they're not as well. So a long answer to your question. Yes, moons have rotation poles. If they have a magnetic field, they would have magnetic poles as well.
Alrighty, so the next thing we're talking about is solar flares, and solar flares are not uncommon at all with our sun. We actually appreciate their effects quite a bit. If you've ever seen the aurora, that's what you're seeing. You're seeing the effects of solar flares, a solar flare is just the sun's magnetic field kind of reorganizing itself. When large amounts of electrically charged materials, which there are a lot of in the sun, are moving around in a chaotic fashion on the sun's surface, magnetic field in that area gets jumbled up and tangled and turns into a mess. Sometimes this tangle comes undone as the charges are like moving, and a large explosion happens on the sun's surface. These explosions are called coronal mass ejections, and they send massive amounts of radiation and particles into space. And sometimes these particles come towards the Earth. Luckily, we can sleep easy knowing that Earth's magnetic field protects us from these solar expulsions, going back to what we were talking about at the last topic too, and in this process generate the northern lights. The charged particles get pulled by the magnetic field, become concentrated at the poles, because that's where they're drawn, that's where the poles, the magnetic field lines meet the Earth, and they collide with our atmosphere to produce that beautiful glow. If a particularly nasty coronal mass ejection were to head our way, though, we might not enjoy the effects so much. While we wouldn't like fry from radiation or vaporize or anything like that, the charged particles could effectively shut down any electronic devices or objects we have. This might not seem terrible, but this includes objects such as refrigerators, hospital technology, GPS, a lot of stuff like that. The charged particles can induce massive amounts of current in power grids and just absolutely destroy them. In one incident, it shut off power to 6 million people in Quebec. So they're pretty devastating. There's also, I like to tell this story, when the telegraph was the main mode of communication, a coronal mass ejection happened and it took down the telegraph system. Like global communication was taken down. You couldn't use it anymore just because those power grids and those transformers were all blown up. So in today's infrastructure, we're very dependent on these technologies. This would be devastating and it could make life pretty difficult for us. Okay, obviously we had to touch on this one. It was really fun to think about, but probably the most unrealistic one to occur. I'm talking about black holes here. We know our own sun won't ever become a black hole in its life, and we haven't noticed any black holes popping up out of nowhere yet. Fingers crossed. But let's say for the sake of fun that one does. If a black hole were to be the size of a nickel, its intense gravitational influence would tear you apart almost immediately, and the Earth would begin to orbit it. Since Earth is so much larger than this black hole, though, the black hole would begin to dig through the Earth as they orbited each other, and the black hole would kind of like hollow Earth out from the inside. Now, let's say, so we don't have to worry about like small black holes. Well, I mean, you do, but that's what a small black hole would do. Now, let's say that an average stellar mass black hole appeared next to the Earth. It would be about a half the size of the moon, and it would pulse with the force of over 300 suns. So quickly we would move towards the black hole, and as you got closer, the pull would become stronger, and you would be spaghettified and turned into a string of atoms, and kind of like Thanos into nothingness. And then you would fall into the black hole. So that would be unpleasant. Now let's say that an average stellar mass black hole appeared next to the Earth, and like if it appeared next to the Earth and not where the sun is, it would be like very much the same process. Like Earth would be torn apart by the tidal forces of the black hole, and again torn to shreds. So unpleasant. And this is a really cool diagram of a black hole. And that's what they would look like. Just kind of for context, that's what a black hole would look like. I thought that was really cool. Now, this is personally my favorite one to talk about. The last possibility that we have today for total annihilation is a gamma ray burst, which I'm going to call it GRB from now on. A GRB is an extremely powerful expulsion from highly energetic events in the universe, such as hypernovas, which is the collapse of an extremely massive star into a black hole. Upon collapse, an accretion disk of charged particles forms around the black hole, and they orbit it, and their effects on particles in the vicinity would form two jets streaming away from the black hole's poles at intense speeds. These jets have large amounts of gamma rays in them, which are very highly energetic and extremely devastating for our planet. This is an image of a GRB detected in a very distant galaxy, barely visible at the end of the arrow in the photo, labeled July 3rd, 2013. That's the GRB. This GRB was intensely powerful, but had little to no effect on Earth. Were a GRB to be within our Milky Way, though, and happen to be aimed directly at Earth, which is also unlikely, it would all but obliterate Earth's ozone layer very quickly, and that would allow devastating amounts of UV radiation into the surface. So this kind of goes back to the magnetic field reversal thing. Cancer, lots of problems. It would also start chemical reactions in the atmosphere that would create this chemical smog that would put us into what they call a cosmic winter, and photosynthesis wouldn't happen anymore. Kind of back to the meteor idea. Plants die, animals die, everything kind of goes down from there. So not kind of like a violent and like Transformers-esque Earth blowing up event like you would think, but it is fairly dangerous nonetheless. And that's actually the last one we have. So
Very cool. So just to touch on a couple of these, because we have said, this is meant to be kind of fun. If this is not likely to happen at all, so we don't want to scare anyone. Thinking of like the magnetic field reversal, we've seen it happen in the past. The thing is, we don't really know what effect it's going to have on us because we don't know how quickly that process happens. If it happens really quickly, we could be fine, other than just needing to update our technology with, where the north and south magnetic poles are. Solar flares, coronal mass ejections, those things do happen all the time, but most of them are not pointed at us, and so we don't have to worry about it. The other good news is we are constantly monitoring the sun, and we see the light from that before the actual stuff ejected by the sun reaches us. We have about a day and a half warning. And so we have systems in place to shut down power stations and shield equipment so that we can minimize the effect that would have on us. So lots of watching there, lots of precautions there. Yeah, black holes aren't just going to suddenly pop up next to us. They just don't work like that. Yeah, so just wanted to bring everything back down a little bit after all of the gruesome, awesome, scary ways that, you know, we could be destroyed, but probably not.
We're much more likely to destroy ourselves with ruining the atmosphere and that.
Yeah, that is definitely more likely to happen. All right, well, we don't have any other questions yet, so if anyone has any other questions, now's a great time to leave them in the comments. And while we give that a few minutes, because there's a little bit of a delay here, and see if any of those come in, let me tell you a little bit about what you can expect this week or over the next week. Nope, that was the wrong button. There we go. On Saturday, we have our rescheduled showing of Exploring Venus, where we're going to take a close-up look at our neighboring planet. Next Wednesday is going to be another edition of Ask an Astronomer. So come hang out with us for a little bit, ask us your questions, and we will hopefully have some answers for you. And then next Saturday, we are going to go on a tour of the moons of the solar system. There are a lot of them and a lot of really interesting ones. In fact, in my opinion, there are some moons that are more interesting than some of the planets. So we're going to take a look at those. A couple of other things. If you didn't see in the pre-show, I guess, slideshow type thing that runs before we get started, or if you didn't see our announcement on Monday, we are now officially open for private shows. And so if you head to our website, there is information on the policies in place to have a private show, including we can only have a certain number of people to maintain social distancing guidelines that we at the university are still required to follow. Pricing, show possibilities, all of that, and including a form to reserve the planetarium for your group. So all of that information is there. We're so excited to bring people back in and somewhat head back to some normalcy. We will still be streaming. We will still be doing our shows because our public shows aren't starting up yet. And we don't know exactly when that's happening. Our aim was for by the end of summer. Things are moving a little bit slower than I would have liked, so we've got some updates going on in the planetarium, and we want all of those updates finished before we reopen. But when we do reopen, we're going to have a lot of new, awesome, fun stuff for you guys. So just stay patient with us, enjoy our live streams, come have a private show in the planetarium if you'd like, and we will hopefully be opening in not too long. We'll see. I don't want to give too much away because I want some of it to be a surprise of what's changing and what's coming up. All right. One other thing, if you didn't know, we do have some awesome t-shirts for sale. You can find a link to our online store in the description. And I bring this up because one of our faithful viewers who is here, I want to say almost every stream, sent us a message that they got their t-shirt and they love it. So thank you so much for that. And we're glad you love it. I'm curious to know which one you got. Because we've got some new designs that just came out as well. So if you want to support us and have some awesome t-shirts, there's a link in the video description for that. All right. Well, I am not seeing any other questions come in, so I think we will wrap it up there. Thank you for joining us, hearing all of the horrible, scary ways that the Earth could be destroyed, but it won't. Learn some new stuff, had some fun, and have a, I guess, wonderful rest of your day. It's a nice day out there, no longer in the 90s, which makes me happy. I don't know, I'm the odd one who likes the cold and snow, so it's fine. All right, I'm gonna stop rambling. Thanks, guys. We hope to see you next time. Bye.